Hello there. This is Rich Whitehouse, and I recently released a new debugger-enabled build, BigPEmu, for my patrons. This is one of the Patreon goals that had been voted up pretty early on, and so I've been chipping away at it for a while now. And I figured now that it's here, it'd be a good idea to do a video and kind of demonstrate my workflow and my approaches to things when I'm, using this debugger and the associated emulator here. And I figured one of the nice ways to demonstrate that would be to basically just kind of recreate the process for one of my test cases that I just recently used to polish this debugger up. Which was reverse engineering the Atari Jaguar BPEG format. Most of you watching this probably already know what BPEG is, but for those who don't, it's basically Atari's equivalent of JPEG. Uses a lot of similar concepts. It's basically a bunch of Huffman encoded blocks of coefficients in frequency domain. So JPEG. And it's got a lot of different variants to it. There are many different versions of the loader which were deployed in retail games throughout the system's lifetime. And I don't think anybody had really gone through and fully reverse engineered or understood even one of them, much less, all of the variants of significance. And so this new version of Noasis, which is basically functioning as the debugger for this debugger-enabled build, also supports BPEG files and supports dumping them from Jaguar ROMs and all that. And so what I'm going to do today is basically kind of walk through the process of identifying a BPEG loader in one particular game. I just went ahead and picked Shut Up and Jam. The Charles Barkley game that never actually shipped, but it does make pretty heavy use of BPEGs. And that one does have a slightly different loader than a lot of them do, so I figured it might be, decent example. And so basically, my process here is, not going to be entirely highlighted because it's pretty easy to cheat with this one because BPEGs, the format itself starts with a 4 bytes identifier and it's just BPEG in all caps, and that makes it pretty easy to cheat, and especially because all of the variants of the loader code also actually check for that BPEG tag, and when they do that they check it against a literal, so if you search for BPEG, you'll find that actual loader code pretty quickly. But anyway, I'll show you a couple different ways of tackling this because I feel bad for just cheating, so I'll show you what I might do if I couldn't cheat as easily as well. Okay, so let's load Sir Charles up here. So you load your ROM, you connect, and first thing we're going to do is just go over to memory here. And you can see you've got BPEG here. The match case will start from address 0. Let the debugger search. And here we go, we found an instance. And the BPEG formats, it's just basically 4 bytes of ID, 2 bytes of width in blocks, and BPEG block size is 16 by 16, so actual pixel size would be the block size times 16. So width of blocks, 2 bytes for height in blocks, and then it's 128 bytes of encoded quantization values for chrominance and luminance, basically. And so this, we take a look at the big Indian UN16 value for that. That would be an awfully large width in blocks. So you can probably make the assumption that this is not a valid BPEG file, and yet there is the BPEG magic. So let's come over and take a look at the 68K disassembly around this address, and voila, this is the data we just found here, this literal comparison. So it's basically saying, oh, A 0 is pointing to the BPEG stream. As you can see, I already came in here and bookmarked this function. But basically, show you how to do that if you want to. You can just right click in here or hit F8 and bring up a nice little bookmark for you. But anyway, so this is the 68K function to decode this thing. And since I already know, normally this would be where you go through and reverse engineer this function, figure out what's going on. I've already done that. And so basically this is GPU RAM. We're moving destination pointer here into this location in GPU RAM. This is the width of the output of an output row in bytes, so we're putting that here. This is the work flag, so GPU is also going to be checking this address, and so on and so forth. We're basically doing a whole bunch of setup, mostly filling in data on the GPU, putting the width and height and everything from the BPEG stream in there, and comes down here. This is where it loops through and it puts all those quantization values. It decodes them against what is generally for each game a hard-coded table, and that is pointed to by, let's see here, this address right here. So basically reading values from this table and then reading the quantization values from the header and writing the decoded quantization values to these two streams as it goes. And then what a lot of BPEG loaders will normally do at this point is they'll kick off the GPU and just stick around for it to do some work. This one is a little different because they seem to have modified things for this particular implementation where it's not just the GPU program, running itself and then stopping the GPU and everything. It's got some other code in there too, and it's handling some interrupts. So it's pushed the BPEG implementation down a little bit, and it's also, I noticed, looping continuously, not actually stopping the GPU once the work finishes. And so that work flag becomes a little bit more important for this implementation as well. But anyway, so, identifying the BPEG loader on the 68K side is the first step. Then we would come over to the GPU and see what's going on there. But of course, as you probably know, the GPU program is going to change a whole bunch of times in a given frame in most Jaguar games because you've only got 4 kilobytes of memory there. All your code has to fit in there, and typically you want to do a lot more stuff, a lot of different things throughout the course of a frame, so you're going to be writing into that GPU memory repeatedly and executing different routines and such, either kicking the GPU multiple times or having some kind of semaphore or whatever. Lots of games do it in lots of different ways. But anyway, so we know where the routine is because we've cheated. So what if we didn't have the luxury of just searching for a literal and immediately finding the routine that we want to deal with? Well, that kind of depends. There are a lot of different ways I tackle things depending on what I'm actually trying to do. If I'm trying to reverse engineer a file format, for example, if I already have some sample data that I'm taking a look at, the easiest thing to do will obviously be to figure out where that is in memory and data breakpoint it. And if you have something kind of open-ended like this, where it's like, well, you've got a bunch of BPEG files, you don't know which one is which, but you kind of like something to start with so that you can identify the code that's dealing with it, you could do something like, okay, let's search for a BPEG that is pretty large. So because it's pretty large, it's probably going to be used for some full screen purpose, and we'll have a fair chance of catching that somewhere in, say, the title and opening sequence. So this one is not very large, as you can see, 12 by 3. Let's keep going. And here we have a nice sizable one. So this one is 24 by 15 blocks, and that would be in pixels 384 by 240. So that's pretty sizable. So let's hit F9, stick a breakpoint on that, and let's go ahead and restart the game. Alright, obviously it was not Sir Charles. Let's keep going. And up. There it is. Alright, so whatever this BPEG is, at this point in the startup sequence, we are trying to load it. So obviously that'd be another way that you could tackle this. Again, A0 is pointing to the data, we just data breakpointed. And for reference, hitting F9 again, that'll automatically go to this breakpoint in the breakpoint list. Or you can just hit Control F9, that'll remove it. And so now that we have identified our BPEG decode routine, we can put a breakpoint on that. And we can reset. And now the initial graphic of Sir Charles, we could, figure out what to do based on that data or whatever. And as you can see, this particular BPEG is located here in memory. So what you could also do at this point is, let's say we want to go ahead and dump this BPEG. So let's say Sir Charles, and let's go ahead and give that a BPEG extension. And we don't know the exact size in the debugger here, so let's just say, dump an assload of data right here. And the debugger will automatically do that for you. And then you could come over here in Oasis. And, like I said, it's already got a BPEG script. So, hey, look, it's Sir Charles. Okay. So, that also brings us to, the right-click context menu in the memory view has a whole bunch of different nice, useful things that you can do in here. And, there are markers and breakpoints that you can use to navigate, as well as bookmarks. And, of course, the find function is very useful. You can also import entire sections of memory from a file. So, you can stop large swaths like that. Or you can, replace just bytes at a time, just poke bytes in there. Often useful for diagnosing things or cheating or, screwing around as you will. So anyway, now that we are looking at, we're stepping through the code where we're loading up a BPEG on the 68K. We can come around to the end of this function. And at the end of this function, so this function is going to be, filling in some more, I believe it's semaphore type data. I don't remember for sure. But like I said, normally we'd be actually kicking the GPU at this point. This one operates a little bit differently. And so we'll step down here, kill that breakpoint because we're done with it. And basically what we want to do is we want to keep on stepping until we get to the point that we know we've loaded up the appropriate GPU program and we are basically going to be waiting on that GPU program to either complete or set the appropriate semaphore or whatever. So this is that point. I've already stepped through to save us the time and put a bookmark there. So let's go ahead and step to here, and now we can come over and we can take a look at what the GPU is doing. So it has just started the BPEG decode routine, and I know that because I happen to know what that routine looks like pretty reliably. I believe the start of it is somewhere right around here, and we take a look at R14. This is going to be basically a bank pointer. It's got a couple banks of values. This is the first series of decodes, and this is the second series. And there is example BPEG loader source floating around out there. I think it's even in the one of the Atari Jaguar SDKs on archive.org. And that will, if you were trying to do something like BPEG, that gives you a big leg up because even though this particular loader does have some differences, it's still very useful to have source reference, obviously. And let's see here. Yeah, even though, so these are, if you actually go to the start of GPU RAM, this is normally where BPEG loader code would reside in a lot of games. It does. Here, obviously, we've got some interrupt handlers first, and the actual BPEG loader code doesn't begin for a little ways down here. We've got a lot of room for data, and again, so right around here is where your relevant GPU program begins. And if you want to see exactly where execution kicks off, you could say, all right, can set a breakpoint here, and we know the appropriate GPU program is already loaded up. So what we can do is we can go to this breakpoint. We can go here in memory and say, all right, here is a bunch of junk that I want to be in memory when I hit this breakpoint. Then we can come in here and say, okay, next unit dates, new data, close all this, and let's just format this nicely real quick here. Alrighty. There's our nice C-style array of code that we would like to have right here. And excuse me while I get the name of the function I've forgotten to do a memory comparison. Alright, so you can call this function and say, I want to pass in my breakpoint data, and I want the code at this address. So basically, I don't want this breakpoint to fire unless the code at this address matches this. So even if you are running a whole bunch of different, GPU programs and what have you, you won't be bothered by any of them until you hit the one that's actually relevant to your interests. And let's get rid of this guy. And we're basically going to toggle these off temporarily. Resume execution. And we'll toggle them back on. Reboot. And here we can see, all right, so now we're hitting our BPEG decode on the 68K, and you can go ahead and discontinue. And now we've hit the very beginning of GPU code as well. Oops. So anyway, again, these are bits about this particular implementation that are unique to this guy. So let's hop down here. All right, and this is where we actually do the more common thing of loading stuff out of those banks. And so anyway, once you're at this point, this is where, again, you begin the arduous process of, actually reverse engineering and understanding things. And one of the more useful things that I would find at this point would be to either just dump out of here. You can go to the base of GPU memory and just say, all right, export to file, and this, put 4096 bytes in here and say, all right, this is Charles BPEG GPU code.bin, and then, you can disassemble that chunk of binary offline or do whatever to it. You've also got your help commands here, and you can go ahead and do a GPU disasm and just dump the code disassembled right there. So again, Charles GPU code disasm.txt, and then take a look at that file. Oops. And again, there's all that, but you've got it nice and for reference, and you can format it. You can do proper label associations. I've actually got an Oasis script that will convert all these jump offsets and everything into actual labels and label all the data reads and stuff like that. So I'll often dump a disassembly file like this, then run that script on it to make all the labels nice, and then I'll actually start going through the formatted labeled one and doing my additional like naming labels, writing comments, and documenting things from that point. So let's see what else here. And again, show some other useful features of the debugger while I'm in here. So I got all these options, and OP dump is another useful one that is integrated with an Oasis here. So you can do OP dump, step a frame, and this will actually automatically, load up everything that is in the object processor at the moment, and it'll start cycling through it. So that is pretty useful. Let's see. Oops. It's quite a bit more useful if you have an actual game scene here. So load something up, and we'll hold F2 to fast forward through the loading screen here. All right, now let's do another OP dump. And as you can see, we've got a lot of different entries in the object processor, a lot of different objects now, and it's cycling through all that stuff. And this is a pretty useful ability, not just for diagnosing what's going on with your own games, but also for taking a look at what other games are doing that you might want to reverse engineer. And if you come down through the list here, you'll see that the actual address of the bitmap is listed right here. So this is the raw, 16 bits per pixel, probably cry16 or something, bitmap in memory right here. And you can also scroll up through the dump text, and you can see the actual location of the objects which were used to dump these bitmaps. So if you come here in memory, you might recognize these. If you're a Jaguar developer, these are the actual object processor objects representing bitmap objects in this case. And that is also quite useful for debugging or reverse engineering stuff. So yeah, I guess that pretty much covers it for the scope of this video. Hopefully you found this useful, and trying to think if there's anything else I want to cover here. I suppose there's the register window here, so let's go ahead and halt this in the debugger. So you've got a fair bit of different functionality that you can make use of in the register window. Obviously it changes depending on the CPU context, and you can say go directly to this address in memory, or See, this looks GPU-ish. You can also go there and disassembly. See, this is obviously pointing to this bit of code, probably either a return address or just a reference to jump there or something. You can also modify the values of registers in real time, which might be useful if you're screwing around with stuff. And you can also set particular registers to be, split, visualized in different ways. The protocol dictates, obviously, the size of the register, but you can tell it to, show it to you in lots of different ways, obviously, and this works on a per register basis, which can be quite useful at times. And yeah, I think that covers general functionality here pretty well. So, all right, thanks for watching, and see you later.